and welcome back to the channel. So in today's video we are going to be taking a look at at a tool that is built into Quartus. That tool is SignalTap. What SignalTap allows us to do is basically implement a small logic analyzer inside of our FPGA so that we can take a look at what's happening inside of the chip. Now we can use this with our FPGAs if we have enough spare resources, because this does require FPGA resources in order to implement it. But before we get started today, if you like the video, please like it. And of course, if you like what I do, please come back and subscribe to the channel. And with that, let's get started. So we're going to open up Quartus here. And today we're going to be playing with a DE1 SoC board. So we're just going to go ahead and create ourselves a new project. And we will put this project into our repo for the channel. And in our DE1 SoC folder, I'm going to go ahead and create a new directory, and we'll call that SignalTap Demo. So there we go. And we'll name our top level the same thing. I got no files. We're going to add our DE1 SoC. And we'll go ahead and hit finish here. So that will create our project. And of course, the first thing we need to do is create our top level. Because there's nothing right now, so we'll hit new. And we want a Verilog file. So I'm just going to say module. I'm going to want some inputs here. So I'm going to create an input called button. I'm going to create an input called clock. An input called reset. And I'm going to do a single output. Actually, I just need it to be LED. There we go. And we'll put our end module there. And we'll go ahead and save this. And if we do a quick compile, we should see that we have those ports that are tied to nothing. So I'm going to go ahead and hit that quick compile button to start analysis and elaboration. Okay, that quick compile is done. Let's go ahead and look at our RTL here, and we'll see that we should have our inputs defined and nothing actually driving them. So let's create some circuits. So the first thing we're going to do, what I'm going to do is basically create a level to pulse using a state machine. So here's the state machine I will be implementing for that. I will feed that pulse into a flip-flop that just toggles the LED on or off based on what was pressed. So let's get started. We need to create a new Verilog file. So let's say module level to pulse. I'm going to have an input of clock, an input of pulse, or an input of level, and an output reg of pulse. Let's go ahead and end our module. So let's go ahead and create our state machine here. So I'm going to name my states no signal, and we'll assign no signal to be zeros. Next up, signal detected. We'll assign that to be a 0, 1. And lastly, we're going to have a state that I'm just going to call hold. and we'll assign that one to a 1, 1. We need to create some state memory. So I'm just going to call that state. And then we need our always block to control the actual state. So always at pause edge of the clock. Begin and end. So, did I bring in? I did. So I want to add one more input here, which is reset. Okay. So we're going to say if we have a reset, then our state is going to go to no signal. Otherwise, we're going to do a case on our state, end our case. So if we are in no signal, and if I get a level coming in, so we have our level going to a 1, then our state is going to go to signal detected. Otherwise, we stay where we're at, right? So state gets state. Okay, if we are in signal detected, if we have level, then we're going to go to our hold state. Otherwise, we're going to go back to our no signal. If we look at our state diagram, that's the link back right there. And lastly, if we are in hold, if we have a level, then state gets state. Otherwise, state is going to go to no signal. Default case, state is going to go to no signal. So that is our state machine part. Now we need to define our outputs. So always at state, begin and end. We're going to do a case on state. And our states are no signal, signal detected, hold, and of course default. So our output, when no signal is detected, we're going to be a 0. When we detect a signal, we're going to be a 1. In our hold, we're going to be a 1, or no, we're going to be a 0, and our default is to be a 0. Let's end our case, and that should be our level to pulse. And then we need one more Verilog file here. We're just going to call this one toggle. We're going to have an input of clock, an input of pulse, and an output of LED. And module, and this is a fairly simple one. We're just going to do an always block, so always at pause edge of clock. Again, end. And basically, if we detect a pulse, then LED gets tilde LED, else LED gets LED. And that's all we really need to do for that. We're just going to toggle anytime we detect a pulse. So let's go ahead and save that one. And then all we got to do is tie all this together at our top level, which is fairly simple. So we're going to say level to pulse. That's U1, and our order was clock, level, reset, and pulse. So we're going to bring in the clock. We're going to bring in tilde button. I'm doing tilde because these buttons are active low on the DE1. Tilde reset. Tilde reset for our reset signal. And then, of course, I need a wire, which I will just call pulse. So let's wire that up. Next up was our toggle. We'll call that one U2. And that one had a clock, the pulse, and the LED. So there we go. Let's save all of that, and let's go ahead and do a quick compile. All right, our quick compile is done. Let's go ahead and check out our netlist viewer. And there's our clock going to both modules, our button, and our reset. We can check out our state machine here. No signal, signal detected and hold. They all look exactly like I thought they should. And then our flip-flop, where the pulses are enabled, the clock comes in, and our Q feeds back to D0. So there we go. That looks pretty good. Now we just need to do some pin assignments. So let's go to our pin planner. Our standard for this D1 SoC is 3.3 volts, so we'll change all of these to that. Our clock is on AF14. We can check the rest of these. So I'm going to put reset on Y16 and the pulse on A14. So reset will go to Y16 and the button will be A14, which just leaves the LED. We'll use LED 0, which is V16. So there's our V16. So now we have all of our pins assigned, and we can go ahead and do our full compile. Okay, there is our system compiled. We'll go ahead and open up the programmer here. Do our auto detect. We need to choose the 5CS EMA5, that is the FPGA. Yes, we want to change it, and let's go ahead and grab our SOS file. And we might as well go ahead and save this setup so we don't have to do it later. And we will go ahead and program this. You can see the board's unprogrammed. And there we go, right? And if I press and hold the button, the light will come on. If I release it and then I press and hold again, the light will go off. Doesn't matter how long I hold the button, we're only going to produce a single pulse per button press. So there we go. That's all well and pretty cool, but that's not the gist of what this video is supposed to be about, right? I said I was going to introduce another tool so that we could see what was happening inside of that FPGA chip. So the way we do that is with a tool called SignalTap, and we're going to add SignalTap to our project here. We're going to go up here to Tools, and we're going to go down to SignalTap Logic Analyzer. And that will open up that tool, which is here. And you can see we come in and we got a bunch of nothing happening. So a couple things we need to set up to start with. We can set up our chain, but it already detected that we're the DE1 and it's already on our FPGA. We need to go grab the soft file for our project. A couple other things we need to set up. Signal logic analyzers need a clock to clock off of. So let's go grab our clock signal. I'm actually, post fitting is fine. So I'm going to grab our clock right there, and that will be our clock. Yes, I wish to change. And the next thing is we need some signals that we want to look at, right? So I can go ahead and list out all of my signals. I can look at our button. We can look at inside of our level to pulse. Actually, I want to change this to post synthesis. There we go. Before we get too far here, let's go take a look at what some signal names are. So we want to look at our post-fitting technology map viewer. And it's going to want me to save that STP file. We'll go ahead and save it into our project directory. Yeah. Yes, I do. Okay. So, if we look at our level 2 pulse, oh, come on, there we go. We've got our clock, we've got our button coming in, right? That's going to both of our A's and our C. We've got our reset. We've got our states. So we've got state no signal flip-flop. And we've got state signal detected flip-flop. So if we look at both of those, that is our state memory, right? That's what we want to look at. So we actually want to look at state tilde6 and state tilde7, that output. What are those signals? But we can also look at, we actually want to look at the flip-flops, not the combinational output. We want to know what the flip-flops are. So we want to look at no signal and signal detected, the name of those two flip-flops, and then the name of this flip-flop is LED. So let's go back here to our STP file. So I want to look at those two state variables, no signal and signal detected. I also want to look at the register LED, and we want to look at the output LED as well. Boom, 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 that should all be good. Let's go ahead and insert those signals. Actually don't need that one. So, and basically we want to trigger on the button being on either edge. So that's our basic setup here. And you'll notice I'm going to go ahead and hit save here. You'll notice it says I need to start a rapid recompile in order to continue, because we need to rebuild the project with the logic analyzer stuff built in. And I can start that by hitting the Start Rapid Recompile, and that will bring Quartus back up and we will rebuild. Okay, so here we go. If we look at our compilation report, I don't know if you noticed, but before we were using 2 ALMs and 0 memory blocks. Now we're using a total of 303 ALMs and 512 memory blocks. So this does take up some resources. Let's go ahead and go back to our SignalTap. And you'll notice now it's saying we have an invalid JTAG configuration. So we now need to program that recompiled soft file into our FPGA. So I will just hit the program button there. And now it's going to say, okay, JTAG's up and ready. We are ready to acquire. So I can go ahead and run analysis. And we're now acquiring. If I bring up our screen here and I press the button, you can see we acquired, right? Let's switch back over here. Our button did that. Our level the pulse, we went from 0, 0, so no signal was a 0, 0. Then we went to a 1, 1, and eventually our LED went 1 right there. And we didn't actually see the pulse out, but we can see it. But we can now see what's happening inside of our FPGA, right? So now the LED went from high to low as I pressed it again. We can run this one more time. And there we go again. And we went from a low to a high as we transitioned through our states. Now again, this is sampled, so the state transitions are going to be exact. Let's see if I can zoom out at all. I zoomed out all the way. I can't hit it fast enough at 50 megahertz to show the button being low and high. But there we go. That's the basics, and we can actually see what's happening inside of the chip with this. So, just to recap, we can basically use our SignalTap Logic Analyzer to see what's happening actually inside the FPGA, which is a very handy tool. So that will let us know what's actually going on inside of our projects. We did a simple level to pulse and basically toggled an LED with that. That's really not an exciting demo, but it kind of gets the point across. And as always, if you enjoy what I do, please subscribe to the channel and like the video if it helps you out at all. And I will see you next time. Thank you.